All right, let's keep going. So, one thing, the derivative of this function here, y equals x to the square root of x. Any ideas how to attack this based on what we've done recently? Just handle it directly with power rule or anything else like that. Yeah, so I mean, and let's just kind of unpack that. Why is taking the natural log on both sides a good idea? Right. So we have a variable and an exponent here. And among many other things, logarithms give us a very convenient way to deal with having a variable and exponent. So if I take the natural log of both sides, I get the natural log of y equals the natural log of x to the radical x. And then the whole reason for me doing that was so I could handle this. All right, is this a derivative that I can take more directly now? All right, how do we do it? So yeah. Right, so the left-hand side, that'll look fairly familiar from last time. What is the derivative of a natural log of y with respect to x? Not 1 over dy dx. Right, so, and just to kind of recap, I'm kind of writing it down in one step, but that really is. The derivative of the natural log of y with respect to y is 1 over y. And the derivative of y with respect to x is dy dx. Right, on the right, we have square root of x times natural log of x. How do we handle that derivative? Product rule. So we're going to take the derivative of square root of x times natural log of x plus square root of x times the derivative of natural log of x. Is the derivative of square root of x something where? Yeah, so I mean, by no means do I think you need to remember or memorize any of these things, but I'm guessing that for a lot of you, some of these just kind of, you commit them to memory the more you do them. So 1 over 2 square root of x times natural log of x plus the square root of x times. So can we do any simplifying? Natural log of x over 2 radical x plus 1 over radical x. And I think this is about as well as we're going to do. All right, so now I have 1 over y dy dx is equal to natural log of x plus 2 over 2 radical x. So we're almost there. What do I need to do to finish up? Multiply both sides by y. So dy dx equals natural log of x plus 2 over 2 radical x times y. Which is radical x. That's correct. Right. So that's just me finding a common denominator. So Anybody else? Any other questions on this thing? All right. That is all for All right, so skipping over section 3.4. Section 3.5 is all about inverse trig functions. Maybe. So I've asked this question before. What kinds of functions have inverses? One-to-one functions. So we know the term. What does it mean for a function to be one-to-one? One input, one output. Do you agree with that? I think that tells us if something is a function, but it doesn't necessarily say that that function is one-to-one. Because I think I could say this if I were to graph out this. Would you say that for any one input I get at most one output back? What do you mean by that uniqueness? Okay, so I'm gonna write down the language. I mean, it's very informal and I think it's valuable. One input, one output. This is a function, or at least an informal way to describe a function. And then if I wanted to, update that to include that one-to-one idea, I like the word unique. So yeah, the only kinds of functions that have inverses are one-to-one functions. So how about these things? Your three, fundamental trig functions: sine of x, cosine of x, tangent of x. Do any of those functions have inverses? So I see a nod. I see a couple of nods. We agree that they all have inverses, right? You've done things involving the inverse of sine and the inverse of cosine, the inverse of tangent. Are any of those functions one-to-one? None of them, right? So what do we have to do? So by definition of what kind of functions have inverses, what kind of functions are invertible, none of those three fit that. So what do we have to do to these functions to make them have inverses, Cameron? Limit them to one period. So let's talk about that. So I'm going to graph sine of x and middle line 1 and -1. Somewhat accurate. Okay. Clearly not one-to-one, right? So we need to get this thing pared down to one period. Does it matter how I do that? Not really. Okay, let's do this then. There's one period. Is that thing one-to-one? No. Okay. So we need to take a little more care on how. Yeah, one period's a good idea because that way it captures the whole behavior of what the sine function does. But I can't really use this. Any other ideas? Pi over 2 to 3 pi over 2. If I restrict it from, why aren't you erasing? Pi over 2 to 3 pi over 2, is this thing 1 to 1? Absolutely. So that's 1 to 1, but I'm going to move this back a little bit just to kind of keep us in line with convention. I'm going to go between negative pi over 2 and pi over 2. You absolutely could define, I mean, you could define it as from pi over 2 through pi over 2, but you'd kind of be the odd person out from the way these things are defined. So we are going to define our new sine function like this. It has a domain of negative pi over 2 to pi over 2, and it has a range of what? 1 to 1. So negative 1 to 1 is important because, I mean, I want this thing to be 1 to 1, but I want to capture all of the possible output values it might have. But to do that, I have to restrict that to, and it ends up not being a full period, right? In this case, it ends up being half a period. Any questions on that? How about for cosine? We've already said cosine is not 1 to 1. We needed to restrict it somehow. I'll just draw from the positive side on here. So I can stop now. We okay with that? So what's that domain and range then? 0 to pi, negative 1 to 1. So this is our new cosine function. We were going to restrict the domain. So we're going to restrict the domain in such a way that we don't restrict the range. So I have a 1 to 1 relationship now with this new restricted domain. Good so far? And finally, tangent. This one, I feel like this one's a little more intuitive because tangent has places where it just is not well defined. That's so pi over 2, negative pi over 2, and then these asymptotes show up every multiple of pi thereafter. And in between these get arbitrarily small or arbitrarily large, depending on where you are. So first of all, where's the range? What's the range on the tangent function? Yeah, it's every real number. And based on, so we're going to keep this centered around an angle of 0. What's a good domain here? Non-inclusive. So yeah, this one, it's a little different than sine because tangent's not well defined at the ends of that interval. Go ahead. Why not? Why so that's not So maybe we can explain why that happens. Can I represent tangent in terms of sine and cosine? So this is true, right? But if we try to do, for example, tangent of pi over 2, what's the sine of pi over 2? 1, and cosine? 0. So that is why there's a problem. Yeah, that's why the tangent function is undefined at those intervals. And basically everywhere the cosine of the argument is equal to 0. Anything else? Yeah, maybe. All right, so sine or inverse sine of 1/2. So let's talk about what inverse functions do. Not remind ourselves of it. Basically, I'm gonna let's name this thing. I want to call it x. So now we're gonna adopt those situations where sine actually has an inverse. If I know the inverse sine of 1/2 is x, what can I say about, what's a corresponding relationship? Y equals 1/2? Oh, okay, I see what you're saying. Yeah, so we could say y equals 1/2. But could I express this information, this inverse sine of 1/2 equals x, using some other function? Like thinking about the way inverse functions work, what's kind of the other way to state this? And I'm trying hard to ask that question without just giving it away. Yeah, sine of x equals 1/2. Because that's what we know inverse functions do. They exchange elements from the input or from the input set, the domain, for elements in the range. So 1/2 is in the domain of inverse sine, which means it's in the range of sine of x. So basically now what we're asking is, what value of x, what angle has a sine value of 1/2? Let's draw your favorite thing in the unit circle. And think about what we just said. Think about how we just restricted the domain of sine of x. Based on that, do I have to look at all 4 quadrants on this unit circle? Which ones can I cut off? It's not the bottom 2. So yeah, quadrant 2, quadrant 3. Because what did we say the domain was of sine of x? So that's, angle 0, pi over 2, negative pi over 2. Over here is plus or minus pi. Yeah, we're restricting ourselves to negative pi over 2 and pi over 2. And we have sine is equal to 1/2. Can I eliminate another quadrant based on that sine equals 1/2? Let me answer that, or let me ask with that. Let me ask another question. What does it mean? What's the sign of an angle mean? Just by definition. Opposite over hypotenuse, right? There's actually a kind of more fundamental definition than that. It's actually based on circles, not triangles. Do you have your hand up or pull it back? Hopefully this sounds familiar. Let's say I have some angle theta. Then basically what cosine and sine do is this. If you have some angle, it's going to project some points onto the unit circle, right? That point is going to have an xy coordinate. And those xy coordinates are going to be cosine theta, sine theta. So basically what the sine of an angle gives you is what that y value is that on that point that you project onto the unit circle. The cosine is that x value. So basically what we're asking for is, we're looking for that where that vertical value is 1/2. If you want to think about it in terms of triangles. We've been calling it x. Opposite 1, hypotenuse 2. Do we recognize that angle? What is it? Yeah, we want to stick in radians, but yeah, pi over 6. So maybe a refresher on kind of how the unit circle works, and because I've already had a couple people ask me about it this semester, I don't waste your time memorizing the unit circle and all the angles in it and all that stuff. There are a lot of patterns and relationships that emerge, and I don't know if we have time to talk about it in class, but if that's something you want to talk about in office hours or over email, or maybe we can do maybe I could shoot a couple of videos for you, but yeah, once you kind of understand the patterns that are kind of going on there, it's a little easier to deal with. Any questions about why that angle is pi over 6? And one thing I want to point out here, if I just started off with this question, what values of x satisfy sine of x equals 1/2? Is there just one? No, there's infinitely many, right? So why in this situation am I only going to give you one? Yeah, the domain's been restricted. Go ahead. Yeah, that's the answer here, basically. The inverse sine of 1/2 is equal to pi over 6. So think about the sine function. Think about what do you input to a sine function? You give angles to the sine function, right? And then it gives you in return some ratio. So the inverse sine function does the opposite. You give it some ratio of lengths, and it returns the angle that gives you that. Anything else? All right, how about this thing? What about the tangent of arc sine? By the way, is that a notation we've seen before? Arc sine instead of inverse sine? Arc sine of x is equal to the inverse sine of x. So we need to evaluate this from the inside out. Let's look on the unit circle again. I'm looking at the unit circle, and I'm looking at, so the first thing we're going to look at is this arc sine of negative 1/3. Can I narrow my search down to 2 quadrants, 1 quadrant? Like, how can I make this easier on myself? Which quadrant is that? Yeah, so we're going to look here, right? So I can eliminate quadrants 2 and 3 because of what? What about the arc sine? Right, so I can eliminate quadrants 2 and 3 because I've restricted my domain to quadrants 1 and 4. And then why can I throw out quadrant 1? Right. So you started off by saying why. Right. And I think, correct me if I'm wrong, I think you said why because sine is all about that. Whatever the second. Oh, the x-axis. Now I have this triangle. Here's my angle just for representation. Opposite -1, hypotenuse 3. But what I want to find is, so I'm going to call this theta. So I guess now what I'm really asking is the tangent of theta. How do you find the tangent of an angle? Sine over cosine, or more directly, since I already have 2 legs of a triangle, or 2, was that opposite over adjacent? Also, yeah, I mean, so many ways these things converge. But just in keeping with this triangle metaphor, since we already started it, we're looking at the opposite over adjacent, right? No, the opposite side, that's -1. We know the adjacent side. Can we find that adjacent side? How do we do that? So I got -1 squared plus, or yeah, sorry, y squared equals 3 squared. So I get 1 plus y squared equals 9. Y squared equals 8. And I get y equals plus or minus 2 radical 2. Based on what I have here, does it make sense to choose positive or negative, one or the other? Should be positive, right? Why is that? Yes, you're looking at an x value to the right of the y-axis, so it should be positive. So this is the value we're looking for. Exactly. So just a quick refresher on kind of how the inverse trig functions and the fundamental trig functions work together. Question? The domain. Anybody want to answer that? How did we? So first of all, the first thing we eliminated, kind of by default, is quadrants 2 and 3. Why are we allowed to throw out quadrants 2 and 3? What's negative in quadrant 2 and 3? Not all of them. Y is positive in quadrant 2. Right. But think about what we're really doing with sine of x. So remember how we restricted our domain? We restricted our domain so that we could look at from negative pi over 2 to pi over 2. So, and this over here is plus or minus pi. If we're restricting our angles to negative pi over 2 and pi over 2, think about where those angles live on the theta circle. Zeros here. Positive. Next question. Why did I not consider quadrant 1? Okay, so all of my sine values are going to be positive up there. So just to kind of show this inverse relationship again, if I have the arc sine of -1/3 equaling x, then that tells me that sine of x is equal to -1/3. And the only quadrant, so of the 2 quadrants that I have, 1 and 4, the only quadrant where I can get negative sine values is in quadrant 4. Good question. Anything else? All right, so let's get into this derivative. So given that y is equal to the inverse sine of x, I want to find dy dx. I could go to the difference quotient, but I'm not going to do that here. So one thing I'm going to remind you about inverse functions is this. We can kind of apply this inverse to the way we do algebra, which means I can do anything I want to one side of the equation as long as I do it to the other. I'm going to take the sine of both sides of the equation. Sine of y equals the sine of the inverse sine of x. What is the sine of the inverse sine of x? It's just x, right? Let me write that down, then I'll kind of unpack it a little bit. So think about now I'll do a concrete example, but think about what the inverse sine of x says. Basically, that means x is some ratio, and I want to know what angle gives me that ratio, right? Once I've found that angle, what do I get when I take the sine of that angle? I better get the original x back. So are we okay that sine of y equals x based on what I have here? Jordan? I'm trying to, so I don't know anything about the derivative of the inverse sine. So I'm trying to manipulate this thing so I can take derivatives of things I know how to take derivatives of, which now I have sine and x. I can take derivatives of these functions. Oh, basically I took the sine of both sides. Sine of that equals sine of that. So just being, I'm just doing algebra essentially. I mean, I can add 2 to both sides, I can square root both sides, or I can take the sine of both sides. Sebastian, you have a question? That was it? Okay. All right, so if we're okay with how I got to sine of y equals x, can I take a derivative here? What's the derivative? I'll do the right-hand side for you. What's the left-hand side end up looking like? That's good. So yeah, this is implicit differentiation, which is always involves the chain rule, like cosine y dy dx equals 1. All right, then if I want to find dy dx, that's equal to 1 over cosine y, right? But I would really like not to have y in this differentiation formula. So let's try to get rid of it. I know that I have some angle y. Let's go back to this relationship here. We had sine of y equals x, right? Does that mean that I can label 2 sides of the triangle like this? Opposite side x, or a hypotenuse 1. Based on that, can I find the missing side? So I'll call it b. You know that x squared plus b squared equals 1. B squared equals 1 minus x squared. B equals square root of 1 minus x squared. I really should call it plus or minus. So let's do this so far. So I got dy dx equals plus or minus 1 over square root of 1 minus x squared. Even that plus or minus, though, we don't like. Now think about this. If I'm looking at sine, what quadrants do I care about? Not 1 and 2, 1 and 4. What can you say about cosine in those 2 quadrants? So I'm just going to draw half the unit circle. Why is the cosine positive in those 2 quadrants? Right. So that means I can delete this plus and minus and just take this. So the derivative of the arc sine or inverse sine of x is 1 over radical 1 minus x squared. First and fourth. No. So b and x. I mean, I squared them, so they could have been positive or negative as far as I know, right? The whole reason for that is that this triangle comes from sine of y equals x. Now think about, we have a definition of sine where sine is defined for all real numbers. At the start of class, we kind of threw that out for this new sine function that's only defined between negative pi over 2 and pi over 2. So because it's only defined between negative pi over 2 and pi over 2, I'm only looking at this right half of this unit circle. Right. And because I'm only looking for angles or outputs between negative pi over 2 and pi over 2, think about what the cosine of angles is. It's the x value. So what can you say about the x values on that on the part of the unit circle I've drawn? They're always positive, or they're always non-negative. Thomas? So sine of y equals x, right? Anything else? Gordon?
I don't understand how you solve the triangle.
Okay, so I'll back up a step. So this sine of y equals, are you okay with sine of y equals x? And this is the question that you asked before. Okay, so this is what I'm giving you is y is equal to the inverse sine of x. Let me just make this a little more general. Let's say I don't know what this function is, I just know this. Y is equal to the inverse sine of x. Or sorry, y is equal to the inverse f of x. Can I restate that using the function f, which I know must exist because I'm calling this f inverse? X equals f of y, right? So this thing right here, this general thing that we just did, that's true for every single function that can be inverted, right? And that includes inverse sine. X equals sine of y. What is the inverse of inverse sine? Just sine, yeah. And that's the one thing that I haven't really focused on, but maybe it's a good thing to focus on now. The inverse, the inversion process in functions is totally reversible. So if f inverse, so what is the inverse of f inverse? Just f, right? So if I invert a function and then I invert it again, I better get back what however the original function was defined. So even though it seems weird to start with the inverse and then ask about what the inverse of that is, that's how we get from inverse sine of x to sine of x. Yeah. That's essentially what I did. Yeah, that's essentially what this is. Yeah, it's going to take you the sine of both sides. Inverse on it. Yeah. And so I'll return your attention. Yeah. That means this. Provided all these things are defined, f of y is equal to the f of f inverse of x. Yeah, that's absolutely fine. It's not something you'll probably do very often. I mean, unless you take like a more proof-oriented course, because we're going to be dealing with specific functions here, but absolutely okay to do that. Question? Yeah, I mean, they have to be, I don't want to say they both have to be positive, but they have to be consistent. So like in the arc sine one we did, I started off with a negative value for sine, right? But that ended up being positive as far as the cosine was concerned. So I don't want to say they both have to be positive or both have to be negative, but basically, if you have nested functions like that, you know, whatever the inner function, that just means the overall function is not defined. Jordan. Look, so answered the first question. Let's just rebuild the triangle. So I think you're okay with sine of y being equal to x, right? Okay, you sure? Okay. So think about what sine of it. So I am implicitly saying when I say sine of y, that y is an angle, right? So I'm saying that y is an angle, and I'm saying that, and just by definition of it in a right triangle, that's equal to opposite over hypotenuse, right? Yeah, so that's opposite side x, hypotenuse 1. And the Pythagorean theorem to, what was that? Any other questions on this? Okay. All right, so what's the domain, first of all, of this function? The inverse sine of x squared minus 1. So just to kind of give us a little layer of support here, I'm going to say that y is equal to x squared minus 1. So if I have this, the inverse sine of y, what kinds of things can y be? So we started off today talking about what the domain and range are of sine of x, now that we've restricted the domain of sine of x. Well, D and R will be the domain and range. What did we say the domain and range were for sine of x? Yeah. Then if I want to compare that to the inverse sine of x, there you go. So what kinds of values can y take? Not quite, because so y, so I know we're calling it y, which we're used to associating with the range of something, but in this case, y is the input to the inverse sine, right? Which means it is restricted between -1 and 1. To leave myself more room. This is not the only thing I want to do on this slide. So we really care about this though. -1 is less than or equal to x squared minus 1, which is less than or equal to 1. Or if I add 1 to all three of those branches, I get 0 is less than or equal to x squared, which is less than or equal to 2. So I'm going to go ahead and remove this, because isn't that always true if I square something? Always going to be at least 0. And this is the part that's a little tricky. If I have x squared is less than or equal to 2, what are the minimum values of x and y that I can have are? Let's start with the maximum, because that's probably easier to think about. Radical 2. What's the lowest? Is it 0? Negative radical 2.
Oh.
Maximum? Square root of both sides. Adding 1 to all three. I'm trying to solve for x in this inequality. So I'm trying to isolate it. The inverse sine? I'm not really looking at it right now, so I'm trying to find the domain. of inverse sine. And since we said the domain of inverse sine was this thing here, from -1 to 1, then, so basically we replaced the question of what's the domain of inverse sine of x squared minus 1. I know x squared minus 1 has to be between -1 and 1. So I'm not really trying to do anything with inverse sine except for make sure that I know what values of x this function actually defined on. Yeah, that first bullet is just I want that set, that interval. Get the next two parts and call it a day. All right, we just talked about how to take derivatives of this thing. So how am I going to find the derivative? Gotta have chain rule. What's that? We could do sine on both sides. I am going to say no to that because we now have a good derivative rule for inverse sine. So I'll just in the margin here, what's the derivative of the inverse sine of x? Which means this is going to be equal to 1 over radical 1 minus x squared minus 1 squared, right? Oh, the derivative, yeah. Which is equal to 2x over the square root of, does this thing do anything good for us? I'll just leave it as is. It might, but I'm not sure. So there's your derivative. And I figure out what the domain of the derivative is then. I actually better stop here. What I will do is post these slides in a bit and I'll have you convince yourself of this. Prove that domain of f prime is negative radical 2 is less than x, which is less than radical 2. Is that the same as the domain of the function? No, it's not the same. So yeah, not including the endpoints, but so it's identical except for exactly 2 points. All right. I think that's it.